We've talked a bit about some extra unwanted signals that we commonly see in the data. And we're going to talk now about how these are handled. We'll see the evolution of a typical interferogram as we pass through successive stages in processing. This processing chain is typical for mining, and initially we're only going to talk about a single interferogram. In reality, however, it would be processed as part of a network of interferograms which overlap in time, which we'll talk about later. This is a raw TerraSAR X interferogram. This is the result when you simply subtract one phase image from another. Hopefully you can see on your screen many hundreds of mainly vertical lines in the image. Each one of these lines is actually a full cycle of phase values called a fringe, and the value for each pixel is indicated by the legend on the right, traversing from 0 to 360 degrees. The left side of the image is what's called near range, the pixels nearest to the sensor, and as you go to the right, further in range, the two path lengths have to change length by different amounts, which causes this effect called the flat earth effect. There is no sign of anything that we might determine to be ground displacement signal, but just as a teaser, this is what we're trying to get to. This is the fully processed interferogram, which I think you'll agree looks very different to our flat earth interferogram. So we have a long way to go. The flat earth effect is easy to model because it's a simple linear ramp, and the model looks like this. Hopefully now you can see thousands of parallel phase fringes marching across the image from left to right. When this model is subtracted from the raw interferogram, we get this. Now the interferogram at least has some structure other than vertical lines. This is called a flattened interferogram. The flat earth phase has been modeled and the model subtracted to reveal something that looks like a contour map. That's because it's dominated by fringes due to topography. If by luck my B-perp was smaller or happened to be 0, then this would be a much calmer image because I wouldn't see any topographic fringes at all. Remember always that sensitivity to topography is a function of B-perp. So how do I get rid of this? Luckily, elevation data is something mines usually have, and it's usually good data and fairly recent. We can take that data, convert it from meters in map space to phase values in radar space, or RDC as we call it, and then scale it appropriately by the B-perp for each interferogram, and this becomes our model of the topography for that specific interferogram, which in this case looks like this. So this is my model of what I think the topography looks like for the specific interferogram in question, according to the site's own elevation data. So this is the site's elevation data pretending to be an interferogram, but only the topographic component. Flicking back and forth gives you a sense of how correlated this model of the topography and the interferogram are. It's not one-to-one, but it's pretty close. Subtracting the model from the interferogram gives us this. Hopefully you're getting a sense of how each stage attempts to explain more and more of the variance in the phase. With the topographic signal removed, this is now commonly termed a differential interferogram. Huge numbers of fringes have disappeared and we can see some structure now, but it seems unlikely that all of this colour variation is entirely due to displacement, as this is many kilometers across. The main feature in the bottom center appears to be what looks like a finger valley system. Even though we just removed the topographic signal, this phase still appears to be correlated with height. This is an atmospheric effect known as hydrostatic atmosphere, which is a phase response due to temperature and pressure. Pressure and temperature both decrease with height, so the phase delay we get from pressure and temperature varies with height. Alternatively stated, when I look at the bottom of a pit in an interferogram, I'm looking through more atmosphere because it's lower down. The top of a mountain should have a lot less atmosphere in the way. So this is a well understood phenomenon, and we can correlate our phase change with our model of the elevation to build a model of hydrostatic atmosphere, which looks like this. Clicking back and forth gives you an idea of how well this model explains hydrostatic atmosphere. And when we subtract this model from the interferogram, we now see this. The phase values are starting to look a lot flatter, mostly dominated by pink, which, as you can see by the scale on the right, is around 90 degrees or so. What we expect to end up with, though, is non-moving areas to be around about 0 degrees phase, which is a light blue. So it seems that most of our interferogram is sitting on a kind of phase plateau. This is also an atmospheric effect, not due to pressure and temperature, but due to the distribution of water vapor in the troposphere. This is a kind of clumpy effect on the scale of a few to tens of kilometers, and this is termed wet atmosphere because hydrostatic atmosphere is often termed dry atmosphere. Unlike the dry atmosphere, there is no equation I can write down that describes or models this effect. It is random over time, and whilst it has some kind of spatial structure, it's not in any way predictable. There are data sources that describe its distribution based on measurements, but right now they are far too coarse to help here. So instead of modeling, I need to make some assumptions and design a filter. If I assume some scale of wet atmosphere, say kilometers to tens of kilometers, and also assume some scale of displacement, say hundreds of meters maximum, I can design a filter to remove this effect. Also in my back pocket, I have the fact that displacement is not random over time. We usually expect it to grow with more time. Wet atmosphere, on the other hand, is random over time. So I can build a filter and make what's called an atmospheric phase screen ready to facelift from my data. Here's what my atmospheric phase screen looks like. Flicking back and forth will show you how the two are correlated. Look at the big yellow area near the top, for instance. One is just a heavily smoothed version of the other. This is a potentially dangerous process. If I'm not careful, I could end up removing displacement signal here, especially if it was subtle and wide scale. Dewatering displacement, for instance, tends to be subtle and can occur on wide scales, and therefore it can look a lot like wet atmosphere. This atmospheric approach then would not be a good option for that application. But most mining displacement, though, tends to be strong and localized, and we know in advance where the large areas are because monitoring campaigns usually have a lot of documented history behind them. But to be safe, we protect our known areas of displacement from filters like this using a mask that says "Don't filter here." Now the data is correctly referenced to light blue on average. In the center, there is some phase variation that has not yet been explained by any model or assumptions thus far. This is mostly displacement. What else is here? Well, the elevation model is not perfect, so we can expect some residual effects where the elevation model does not agree with reality. There will also be residual atmospheric effects, Sometimes soil moisture gradients can cause a phase difference. Here, changes in soil moisture over time change the dielectric properties of the ground, and therefore the reflectivity of the signal. At some sites, snow and ice will be an issue, and we'll talk about that later. Finally, some noise is unavoidable. More on that later also. So this is a summary of the story so far. I've arranged this into rows representing each of the stages I talked about. The interferogram is on the left, the model in the middle, which is subtracted, and the result is on the right. If the models are meaningful, the expectation is a reduction in phase variance at each stage. So in the top left, the interferogram began its journey as a simple phase difference of two SAR images. The flat Earth effect dominates, which is easy to model as a ramp and subtract. The next biggest effect was topography, because I had a non-zero perpendicular baseline. After some reformatting, we effectively subtract the site's elevation data to get rid of most of that. Then hydrostatic or dry atmosphere is modelled and subtracted, and then finally wet atmosphere is filtered by removing large-scale clumps of phase, and we have no effective model of that or independent measurements characterizing it, so we are forced to carefully filter it out. This is about as far as we can get with individual interferograms. But actually, this data would be processed as part of a network of interferograms that overlap in time. I then have more options for addressing effects like noise or errors in the elevation data, and that is the subject of the next lecture.